Hello everyone, welcome to our advanced AI presentation. Our selected paper is Predictive Sampling with Forecasting Autoregressive Model. Here is the team members of this presentation. I am going to cover the introduction part. So, autoregressive models currently hold a state-of-the-art performance in likelihood-based modeling of image and audio data. Generally, neural network-based arms are designed to allow fast inference, but sampling from these models is impractically slow. This paper proposed a new algorithm termed predictive sampling, which accelerates discrete arm sampling, keeps autoregressive structure intact, and samples from the true model distribution. They proposed two variations of predictive sampling, namely sampling with arm fixed point iteration and learned forecasting modules. Effectiveness is demonstrated in two settings: explicit likelihood modeling on binary MNIST SVHN and Cipher10, discrete latent modeling in an autoencoder trained on SVHN, Cipher10 and ImageNet32. These are the name of dataset which will be explained by my next team member. This figure shows the overview of predictive sampling, a sequence so far of autoregressive model samples x0, x1 till xi-1 is extended with forecast of x tilde I, x tilde I plus 1, and so on. This is actually given as input to the arm. The arm has strict triangular dependency. So the first output of x not I, which is this one, is always valid. The conditioning consists only of arm samples. If the forecast x tilde I is equal to x not I, the next output x naught I plus 1 is also valid, as autoregressive models always rely on the lagged value of the previous state.
Now let's look at the overall roadmap of the AR model-based research work prior to our reviewed paper. The first work on AR model was in the year 2000, though for a decade after that there is no mentioned work following the year 2010 due to the growing use of data capturing electronic devices. Data deluge happened and the famous datasets like MNIST, Cipher10 were created, and the related researches didn't stop after that. The paper NAID, published in 2011, is considered as one of the earliest neural network architecture of AR models. In generative modeling, KNN-based likelihood methods can be classified broadly into these three categories: AR model, virtual autoencoder, and flow-based. Among them, PAE and flow-based works are very efficient for fast sampling, but their likelihood performance is not up to the mark. Numerous research works have taken place from 2015 to 19 to increase the likelihood performance by refining training objectives and network architecture improvisation. AR model-based architecture outperformed the other two methods in those works. Now, the limitation of AR model is slow sampling time. In 2017-18, student network use distillation was proposed to speed up the sampling time, but it couldn't preserve the model structure. To keep the model intact, hashing and activation strategies were included with AR model in next researches. But there the problem of large memory overhead arises. Compared to that, our reviewed paper doesn't use any extra memory. In 2018, a language model was proposed which predicted the output using greedy decoding method to save the runtime, whereas our presented paper used sampling from model distribution. My next groupmate will give you the overview of this proposed method.
An autoregressive model, or ARM, suggests the universal probability model where X is a variable in a discrete space for 8-bit images and D is the dimensionality of data. For predictive sampling, the authors tried to parallelize ARM interface to obtain a log likelihood for every variable in parallel. During this process, for a sequence of n number of correct forecasts, n recomputations of autoregressive function are saved. Predictive sampling algorithm outputs the vector x that contains valid samples up to position I. A forecasting function f is used to compute the most probable future sequence. It is added to the forecast vector. The autoregressive model computes an output sequence for future time steps in parallel. If a forecast equals the sampled value, the position I is incremented without any additional inference call. This process repeats until a forecast is not equal to the sample value. When the forecasting function does not agree with the ARM, the last valid output is written to the vector x and the next iteration of predictive sampling starts. This whole process is repeated until all variables have been sampled. There is unpredictability for each dimension brought by the sampling step, which may limit the number of correctly predicted variables. To solve this issue, the authors used a deterministic function conditioned on random noise epsilon to reparameterize the sampling procedure from the ARM. It can be done using Gumbel-Max trick. In order to keep the computational cost of forecasting function low in case of a new number of iterations, the ARM representation from the previous iteration of predictive sampling is shared with the forecasting function. The first forecasting method, ARM fixed point iteration algorithm, uses a function which is a combination of two things. One, any forecast obtained using the ARM reparameterization where noise is isolated. Two, the predictive sampling algorithm. The future outputs are automatically used as forecasts. The algorithm converges in at least D steps. ARM fixed point iteration reuses the ARM output that may depend on forecasts from previous iteration, which may turn out to be incorrect. This might lead to cascading errors. As solution, the authors introduced learned forecasting. They used forecasting modules or small neural networks that are only conditioned on available valid representations. The representation is shared and trained jointly for both the ARM and the forecasting modules. After training, forecasts can be obtained via the forecasting distributions and reparameterization noise.
In this experiment, the authors have used 4 different datasets, such as MNIST, SVHN, Cypher10, and ImageNet32. For the first 3 datasets, they have used the standard test split as their test set. For ImageNet32, they have used the validation set as their testing data. For MNIST and SVHN, they have used 5,000 images from training set as their validation set. For Cypher10 and ImageNet32, they have used random sampling to obtain the validation set from the training set. The authors have proposed 2 different approaches for this experiment. First one is predictive sampling of image data, where they use 3 different datasets. They use the same architecture for all the datasets except for MNIST to prevent the overfitting. In terms of the autoregressive model, it was optimized using log likelihood objective. The performance was reported against bits per dimension or BPD. After 200k iterations, the performance was captured against BPD. In terms of the forecasting modules, a lightweight network architecture was used to forecast T future timestamps. A triangular convolution is applied as the hidden representation of ARM. Depending on the dataset, T value was set for the forecasting modules. The second approach was the predictive sampling of latent variables. Here, they used autoencoders with a probabilistic latent space. However, they separate the training of autoencoders and ARM. First, they train the autoencoder for 50k iteration and freezes the weights. Then they use the weights to train the ARM for another 150k iteration. Finally, they check the performance against the obtained MAC values. The next presenter will be discussing about the performance.
Next, let's look at some experimental results presented by the authors. Pixel CNNs were trained on images from binary MNIST, Cypher10, and SVHN. Results are reported in batch sizes 1 and 32. The baseline performance is given based on 1-by-1 sampling. For binary MNIST, the authors added 2 simple predictive sampling baselines, one that always forecasts zeros, which is the most common element in this dataset, and one that always repeats the last sampled value. We can see that fixed point iteration beats the baseline by substantial marking. Further improvement on this is done using small auxiliary forecasting networks indicated in the table as plus forecasting, where t equals to 20 means the auxiliary network forecasts 20 future time steps. Now, while for binary MNIST, this does lower the needed number of ARM forward passes for batch size 32, the computational overhead of running this function increases the time, negating the benefit of this additional forecasting. On CFER10, fixed point iteration also outperforms the baseline. But unlike in binary MNIST, auxiliary forecasting harms the performance. Results on SVAsian and a 5-bit version of CFER10 is also shown in this paper, and they show a pattern similar to CFER10 8-bit version. The authors have also shown a visualization of where forecasting mistakes can take place, and for binary MNIST, this is closer to the digits as presented by the red marks. Finally, the authors trained pixel CNNs on the latent space of discrete autoencoders, and the results are fairly similar to the image likelihood model. We see that fixed point iteration works best and forecasting doesn't improve the result. The forecasting mistakes in latent space were also shown in the paper.
Hello, I'm Ipshita. I'll be talking about the limitations of this paper. The ARM inference used in this paper uses a formulation to obtain a log likelihood for every variables in parallel. However, this setting fails to parallelize the number of forward calls for naive sampling from ARM. The models introduced on this paper is based on a discrete setting. Using this model in a continuous setting is subjected to numerical errors. The ARM fixed point iteration method uses all previous samples to make predictions on the following sample. So presence of an invalid sample in the previous forecast can make the current forecast invalid. In the learned forecasting model, the sampling are only conditional on available valid information. Due to the slow sampling process, the training of the forecasting modules is done only on samples from the data distribution instead of using samples from a model distribution. The ARM dependency structure is from top to bottom and left to right. So the wrong values in the pixel of the left columns affect the outputs of the preceding pixels. So while performing on a complicated 5-bit CIFR data, more mistakes are found in the top row and on the right side of the image. That's from my part. Thank you everyone for